Hello, welcome to this video. We'll be showing you the SoundCheck sequences that implement TIA standard 920-B. I'm John Baer, I'm developer of those sequences. I'd like to tell you a little bit about them and show you how they work, but first I'd like to say a little bit about the standard 920-B. It applies to handsets, headsets, and speakerphones and makes use of either hats or a mouth simulator and various microphones. It's comprehensive enough that it applies to almost any communication device. The sequences themselves implement the clauses in the standard. They cover almost all the important performance aspects of the phone. So, without any further introduction, let's see what's in the sequences. When the 920 sequence package is opened, you can see a list of all the sequences that are inside. First on the list is a setup. This is usually run before you test a new device. You can tell the system if it's narrowband or wideband, if it is a headset with two receivers or a speakerphone, and that kind of thing. There are two master calibration sequences. One applies to hats. It calibrates the ear and the mouth simulator. Another one applies to standard mouth and microphones. That would be used for testing speakerphones. The first group of sequences with the letters HN in the name all apply to handsets. These names apply more or less to the standard clauses. However, in a couple of cases, for example, receive, send, and side tone, several measurements in the standard are combined in one sequence. In a similar way, there are many sequences with the letter HS in the name that apply to headsets. The headset measurements are quite a bit like the handset measurements with one important difference. In most of these, you will be asked to make more than one measurement by removing the headset from hats in between and replacing it, and then taking an average of the results. Again, the name of the sequence follows the format of the standard, but there are some that have combined measurements included. For speakerphones, there are several sequences that have the letters SPK in them, and again it more or less follows the structure of the standard. You'll also find several sequences with the letter S in them. These are subsequences that normally are not run by themselves, but they're used by sequences above here to make them run a little bit better. If you go down the list, you'll find a couple of legacy versions of the echo test. This is not something that you would normally want to run unless you're required to do so. It uses an older test signal. It runs just fine and is accurate, but the test signal that was used is not so good as real speech, which is used in the current version. Finally, there are 4 extras here that enable you to quickly look and see if the mouth simulator is still in calibration without actually going through a full calibration sequence. This is a typical setup for testing speakerphones according to TIA-920-B. In this case, the lip ring of the mouth is 50 centimeters from the device under test, and on the other side, the microphone grid is also 50 centimeters from the device under test. In this view, you see the speakerphone oriented towards the mouth, and this is the arrangement for sending measurements. When it's time to do receive measurements, we can turn the speakerphone 180 degrees and point it towards the microphone to do the receive measurements. This is a very typical setup for a moderate-sized speakerphone. Different devices might require different setups, but this is typical, and if you're not sure where to start, this would be a good place. When first opening these sequences, it's a good idea to start with this one called Setup, and we'll walk that through in just a moment. But first, let's look at what all is in the package. There is a calibration master sequence that applies to hats. It calibrates the ears and the microphone and the mouth simulator. There's another master calibration sequence that applies to a standard mouth simulator and a microphone. That would be used for speakerphone testing. If you're testing a handset, there are several sequences with the letters HN in the name. These follow the structure of the standard, and it's easy to keep track of where you are because of that. If you're testing a headset, in a similar way, the letters HS are in the name, and again, there's several tests that follow the structure of the standard. Although in some cases, one of the tests in this sequence actually performs two or more tests that are listed in the standards. When testing speakerphones, you'll find that the name SPK is in the name of the sequence, and again, there are several of them following the structure of the standard. There's a couple of sequences that have the letter S in. They're not intended to run by themselves. They're subsequences that the larger sequences above use during part of their running. There's also some subsequences that apply to calibration. Again, these are not intended to be run on their own, but they need to be there because the master calibration sequence will use them. There are a couple of legacy measurements of echo using a different test signal. I'd recommend you don't use those unless for some reason you're required to. And there's a couple of extra sequences here where you can simply verify the calibration of the mouth with male or female signals without actually having to recalibrate. Okay, so that's what's in the sequence. Let's see what happens when we run the setup sequence. Let's start. The standard applies to narrowband, wideband, and also dual band devices that are operating in narrowband or wideband mode. The device we're going to test is a wideband device operating in wideband mode. So we select 3, and that is confirmed. And now when we look at receiving response, if we're testing a handset or a headset, we need to translate the measurements picked up at the drum of the hats. We need to translate that to either the free field or the diffuse field. The default here is free field, although the standard allows both. So we'll select that and confirm it. Then we need to tell the system how many ears we need to use on hats. If the object has left and right receivers, for example, a headset with 2 receivers, we'd click yes. But we're going to be testing speakerphones, so we're going to click no. And that is confirmed that our testing device is either a handset or a speakerphone. So yes, we will confirm that. And now we can actually save this information to the master test report that is important to us. We're going to be testing speakerphones, so we'll say no to handset. We'll say yes to speakerphone. We're going to put the word demo in the file name. And when we click OK, we get a chance to write some comments, if we'd like to, that will go in the report itself. Then when we click OK, there will be some interaction with Excel to save that information in the master test report. We're not testing headphones today, and so we will not save anything to the headset master. So that is the setup. Once you've completed the setup, you do not need to do this again until you change the bandwidth of the device, the translation, or something in the test report. Let's say you want to test a different device and you want to create a new test report. You may want to put this information in that test report, in which case you could go through this sequence again and put that information in. So this is finished. We're now ready to go on to one of the measurements. Receive, frequency response, and level. When the measurement starts, we get a verification of the bandwidth of our measurement. If it's okay, we can go ahead. And now here is a reminder about the position of the free field microphone. Also about the device volume control put to nominal setting. If we don't know what that is, we can find that out from the measurement and repeat.
On the back of the wide chair. A pound of sugar costs more
The signal you're hearing now is a 4-sentence segment of IEEE male speech. It's used to condition the device into a stable
The
state.
jacket hung on the back of the wide chair.
The repetition of those 4 sentences is actually used for the measurement.
Too high for the couch.
The ship was torn apart on the sharp reef.
The measurement didn't pass. The level is okay, but the frequency response is not. If you look at the upper left-hand graph, you can see a solid line that is the measurement in third octaves. It does not pass the mask. For information, there's a dotted line showing 12th octave measurement. And because they go together closely, that shows us there's not too many reflections in the room where we did the test. In the lower right is the waveform that was used for conditioning. That looks good. And in the lower left, the waveform that was looked for the measurement. That also looks good. So this appears to be a valid measurement, and now we will save the data. We could simply save the parameters in a simple Excel sheet, but instead we're going to put the data into a speakerphone master report that is formatted in a very nice way. We can add a word to the name of the file, could be whatever we type here, but we can also add comments that will go into the test report itself. It could be something about the test conditions, the volume control setting, or maybe something special. After some interaction with Excel, writing the data to the master report. The sequence is now finished. Receive volume control measurement. First, a reminder about the bandwidth. If it's okay, we'll go ahead to the next. This sequence is measuring receive frequency response 3 different ways. The volume control settings will be changed, and the stimulus level to the device will be changed. The idea is to find out if the device has sufficient output at various level conditions from the line or volume control settings. And now we have a reminder of the microphone position and to set the receive volume control device on at least 70 dB. If we don't know how to do that, we'll find out from the measurement and we'll be able to repeat.
The jacket hung on the back of the wide chair.
A pound of sugar costs more than eggs.
The first playing of the IEEE male speech, 4 sentences, is used to condition the device to make sure it's in a stable state. The second playing is used for the measurement. In this test, the stimulus level is minus 20 dBu, which is exactly normal. We're looking for a level of just above 70 dB, which we have. The frequency response looks okay, and the waveforms look normal, so we're going to accept that measurement. Now we want to know how to get at least 65 dB when the stimulus level is really low, minus 35 dBu. That amounts to very, very quiet speaking by the party at the other end. We didn't change the volume control, so when we get the results from this measurement, it's probably going to be too low. But we want to see what it is to make sure that we have some idea of how to adjust the volume control. Okay, the level we measured is 57 dB. That's quite a bit below 65. So we need to make a big change in the volume control setting. Since this is a USB device, we're going to set the output from 50 to 100 and measure again.
The jacket hung on the back of the wide chair.
A pound of sugar costs more than eggs.
The coffee stand is too high for
Again, the
couch.
purpose of this test is to make sure that the device has sufficient output when the incoming signal is really, really
A
low.
pound of sugar costs more than eggs.
The coffee stand is too high for the couch.
The ship was torn apart on the sharp reef.
So our output level is just above 65 dB, as we would want. So this measurement appears good. We will accept it and go on to the next.
The jacket hung on the back of the wide chair.
One sentence was used to condition the phone, and then there's several seconds of silence during which the received noise is measured. If you look at the numbers in the box, you can see that the received noise is 24 dBA. That's quite a bit below the necessary level. The single frequency interference is 11 dB. That's pretty good. Single frequency interference could be a tonal artifact of some kind that you'd see on that red line, which is the spectrum. The tolerance for this is the dotted line above it. The waveform on the right shows the one sentence that was used for conditioning and the noise that was measured in the graph and the numbers we just saw before. So a few milliseconds after the conditioning, the noise measurement is taken. Now we have a different condition. A very strong signal of minus 10 dBm
The jacket hung
is
on the
going to
back
be
of the
sent
wide
to the
chair.
A
device,
pound of sugar
and we
costs
need to
more
know
than
if the
eggs.
volume
The
control
coffee
can
stand
be
is too
set
high
so
for the
the
couch.
The ship was torn
output is
apart
not
on the
too
sharp
loud.
reef.
We didn't
The
change
jacket
it
hung on
before
the
the
back of the
measurement,
wide
so we
chair. A
expect
pound
this
of
one
sugar
to
costs
fail,
more than
but we'll
eggs.
look
The
at how
coffee
much it
stand is
failed
too high
to
for the
get some
couch.
idea
The
of
ship
where
was
to set
torn
the
apart
volume
on the
control
sharp
again.
reef.
It should be below 70, but we have 79. So we're going to make a big adjustment again on the volume control. This is a bit of guesswork, but right now let's take it back to the nominal level of 50, and let's see if that's enough.
The jacket hung on the back of the wide chair.
A pound of sugar costs more than eggs.
The coffee stand is too high for the couch.
The ship was torn apart on the sharp reef.
The jacket hung on the back of the wide chair.
A pound of
Again,
sugar
the
costs
purpose
more than
is to make
eggs.
sure
The
the
coffee
volume
stand
control
is
can
too
be
high for the
reduced
couch.
enough
The ship
so
was
that a
torn
loud
apart on the
incoming
sharp
signal
reef.
doesn't blast the listener. Okay, now we have 71. We're close, but not quite there. Let's look at the volume control again and lower it just a wee bit more and remeasure.
The jacket hung on the back of the wide chair.
A pound of sugar costs more than eggs.
The coffee stand is too high for the couch.
The ship was torn apart on the sharp reef.
The jacket hung on the back of the wide chair.
A pound of sugar costs more than eggs.
The coffee stand is too high for the couch.
The ship was torn apart on the sharp reef.
And now we did get the level below 70, so this is an indication the volume control does have enough range. Here we have a summary of those measurements, and overall it passed because the levels are good. For the standard level, we're a bit above 70. For the quiet level, we're a bit above 65, and for the loud level, we can be below 70. The frequency responses you see in the upper left are parallel to each other because the volume control was changed for each of the three measurements. They should look like this, parallel to each other. In the middle stack, you can see the individual received measurements. The solid line is the 1/3 octave, and the dotted line is 12th octave. Since they lie pretty close on top of each other, it indicates few reflections in the setup. In the right-hand stack, you can see the waveforms for all three measurements. And now we can review the results of the noise measurement. Received noise is good. Single frequency interference is good. The difference between single frequency interference and the test is 10 dB. This is a very good margin. Now we'll save to the master report. Put the word demo in the file name, and here we can write test information. Probably you would want to write down the volume control settings for the three conditions. That would be very useful. After interacting with Excel, the test report is made, and we have a reminder that we've been messing with the volume control. So we need to go and set it to the nominal. We wrote down what that was, so we can just do it now without actually doing another measurement and say, okay, we're now ready for further tests. And this sequence is finished.
The jacket hung on the back of the wide chair.
A pound of sugar costs more than eggs.
The coffee stand is too high for the couch.
The ship was torn apart on the sharp reef.
The jacket hung on the back of the wide chair.
A pound of sugar costs more than eggs.
The coffee stand is too high for the couch.
The ship was torn apart on the sharp reef.
This is what the sending measurement looks like. The method is very similar to receive, And so the results are a little parallel as well. This one passes because both the level and the frequency response are just fine. In the frequency response graph, you can see the third octave in solid, and that fits in the tolerance. You can also see the 12th octave in dotted, which means that there's not too many reflections in our test setup. If we go to the bottom right, we can see the waveforms from the conditioning sequence. We can definitely see 4 sentences there, and we can definitely see the 4 sentences in the measurement sequence. So this one is just fine. And so we'll say, yes, it's okay, and then we'll go about saving, not to a simple Excel sheet, but to the master report, as we've done with other sequences. Again, we can put comments here about the test, in particular, if the sending device has a volume control that needs to be set. That might be something to put in here. And then once that's done, the Excel sheets are written, and the sequence will come to an end. The sequence is now finished. Speakerphone echo. At the beginning of the sequence, we have the reminder about the bandwidth it's set up for, and we're wideband, so that's good. The echo is actually made by a metric called TCLW. I'll explain that a bit later. And it's normalized by use of the speaker receive level and send levels that we measured previously. They were stored and will now be recalled. In this measurement, you have the option to run a long conditioning cycle, which is 8 sentences going back and forth between sending and receiving direction, alternating male and female. The object here is to make sure that the device is in a stable state.
The jacket hung on the back of the wide chair. The jacket hung on the back of the wide chair.
So delays were measured so that these stimulus signals can be lined up.
The jacket hung on the back of the wide
Sending.
The coffee stand is
Receiving.
too high for the couch.
A pound of
Sending.
sugar costs more than eggs.
The ship was
Receiving.
torn apart on the sharp reef.
The coffee stand
Sending.
is too high for the couch.
The
Receiving.
jacket hung on the back of the wide chair.
The ship
Sending.
was torn apart on the sharp reef.
A pound
Receiving.
of sugar costs more than
Conditioning
eggs.
is done.
The jacket hung on the back of the wide chair.
A pound of sugar costs more than eggs.
The coffee stand is too high for the couch.
The ship was torn apart on the sharp reef.
The jacket hung on the back of the wide chair.
So as in some of the other
Sugar costs more
sequences,
than eggs.
the IEEE
stand
speech
is too
segment
high
is
for the
played one
couch.
time for
The
further
ship was torn
conditioning,
apart on the
and the
sharp
measurement
reef.
is performed on the second repetition.
The jacket hung on
On
the
the
back
left-hand
of the wide
graph,
chair.
you can
pound
see
of
echo
sugar costs more
frequency
than
response with
The
a
coffee
solid
stand
line.
is too high
This will
for
be
the
performed
couch.
3
The
times
ship
at 3
was
different
torn apart
stimulus
on the
levels.
sharp reef.
Echo
The
frequency
jacket hung on the
response
back of the
is
wide
the signal
chair.
coming back
Pound of
from the
sugar costs
send
more than
direction
eggs.
out of the
The
dot
coffee stand is too
relative
high for
to
the couch.
the stimulus
ship
that
was
was
torn
sent to the
apart on the
dot
sharp
in the
reef.
receiving direction.
The jacket hung on the back of the wide chair.
Now, if the
Pound of sugar
device
costs more
was
than
linear
eggs.
and
The
noise-free,
coffee stand
all of
is
these
too high
frequency
for the couch.
responses would lie on
The
top
ship
of
was
each
torn
other.
apart on the
But
sharp
they do not. And in this case, it shows that most of what's being measured here is actually noise.
Coffee stand is too high for the couch.
You really can't see it from the waveform on the right,
sharp reef.
but there is a little noise that's coming back from the device, and that more or less is contaminating the frequency response, except in this lowest level, in the dotted blue curve.
We tried to replace the coin, but
Sending
failed.
conditioning,
Drop the 2 when you add the
receive
figures.
conditioning,
The set of china hit the floor with
Sending.
a crash.
We tried to replace
receive,
the coin, but failed. The jacket hung on
Send.
the back of the wide chair.
The set of china hit the
Receive.
floor with a crash. Drop the 2 when
Send.
you add the figures.
The jacket hung on
Receive.
the back of the wide chair. We tried to replace the coin, but failed.
Now these measurements will
China
be
hit the floor
performed
with a
just
crash.
as the male
The jacket
speech
hung on the back
measurements
of the
were
wide
performed.
chair.
Drop the 2 when
One
you add the
time
figures.
playing back
tried
the
to
test
replace the
signals
coin, but
for
failed.
further
The set of
conditioning,
china hit the
and the
floor with a
second time
crash.
for
The
measurement.
jacket hung on the back of the wide chair.
Drop the 2 when you add the figures.
And again, on the upper left, we have echo frequency response. The yellow curve is with a stimulus of minus 10 dBm 0.
We tried to replace the coin but failed.
The set of china hit the floor with a crash.
The jacket hung on the back of the wide chair.
Drop the 2 when you add the figures.
So now you can see the second measurement is at minus 20 dBm 0. And there's a little difference there, so there's some true echo.
We tried to replace the coin but failed.
The set of china hit the floor with a crash.
These frequency responses will be used to calculate terminal coupling loss, weighted terminal coupling loss, TCLW. And I'll explain a little bit more about what that is later. So on the left we have the male information, and on the right it's female. If you look at the frequency response for male echo on the yellow curve and take an eyeball average, you will get approximately minus 70 dB. Change the sign and you get approximately plus 70 dB, which is the TCLW. Similar on the right is the information for female. The box at the bottom shows how the normalization was done. The idea is to correct the measurement to what it would have been if the sending output level and the receiving output level were exactly nominal. Some authorities do not recommend doing this, but it's in the TIA-920 standard. You can choose not to do this if you prefer, or follow the standard and perform the normalization. Now we can also take a look at the waveforms and see if there were any noise bursts of any significance during any of these waveforms. There are some visible, but they're pretty small. So mostly what we're measuring here is noise coming back with an occasional burst, like you see in the lower left graph. That would be the male echo at the lowest level. In a similar way, you can see something on the lower right from the female echo measurement. There's a little blurb around 3 seconds. As before, we can save to an Excel sheet or to the master report. We'll use the master report as before and put any notes here about the conditions or anything else that we've observed during the test. Once we click that, the Excel sheets will be generated, and when that's finished, the sequence is done. And now we are finished. Send directionality. This is a measurement of send frequency response and level performed at several different angles and then compared to each other. The idea is to see if the phone is well usable over a wide range of angles on the front side. Since the frequency response measurement is the same that you've seen before, we won't actually go through it, but I'll sort of summarize the process here. The first is to set the phone up at 0 degrees and measure send frequency response. If you need to reset the volume control, you can redo that one until the volume control is set properly. Then you'll get a prompt to move the phone to the 30-degree position and measure again, and so forth for the others. After that's done, you will then see the calculations for send directionality. So now we'll skip to the end and look at that. When the measurements are done, you'll see a set of frequency response curves like the one on the upper right. All 5 positions frequency responses are on the same graph, and you can see pretty easily that they're not that different from each other. The solid line is the 0 degree reference. From those response measurements, the overall level is calculated. That's shown in the upper left box. There is a little tolerance of plus minus a few dB, and the difference that you see, send level directionality, is the difference in level between that particular angle and the reference. And you can see they're all pretty small, so all 4 pass, and the entire test is passed. It means that the sending response and level from the front side of the phone is about the same at all these various angles. At the end, you can save the data to a simple Excel sheet or to the test report, just as we've done for the other sequences. After that is complete, then the sequence is finished. Receive noise and single frequency interference. First, check the bandwidth setup. These measurements should be made with volume controls set to nominal. If you don't know where that is, you can perform measurements and find out. There's a conditioning signal before the noise measurement. Minus 20 dBu is the default.
The jacket hung on the back of the
Now there will
wide
be a full
pound of
chain
sugar
of
costs more than
IEEE
eggs.
speech sentences
The
played
coffee stand
for
is too
conditioning
high for the couch.
to get the device in
The
a
ship
stable
was torn
state.
apart
And
on
then
the
one
sharp
more
reef.
sentence.
The jacket hung on the back of the wide chair.
And immediately after this sentence, the noise will be measured. The box in the middle has the measured metrics. Received noise, 23 dBA, is well below the tolerance. Single frequency interference, such as what you see around 600 and 700 hertz, is low, and it's low enough that it passes the requirement. In the graph, you can see that the white line and the red line are a spectrum, the white being transient noise, that is just right after that last speech stops, and the red is steady state, which is a longer period after a pause of 5 seconds. They both are passing the requirement. In the waveform, the red is the steady state noise, the white is the transient noise near the end of the conditioning signal. So, as before, we can save to a simple Excel sheet or save to the test report, which is what we'll do now. Again, we can put in comments or remarks about the volume control setting or anything else that will help you understand the test after it's over. And when the Excel sheets are written, the sequence will be done. Receive distortion at the nominal volume control. First, check the bandwidth setup, and if that's okay, take the next steps. Make sure that the volume control is at nominal, and you can do a measurement to find out where that is if you don't already know. Distortion measurements use two different kinds of conditionings. One is a complete sentence that comes before the chain of distortion measurement bursts. The second one is a syllable that comes before each individual noise burst. And the noise bursts are the signal that the distortion is made of, and that level is also specified here. These are the default TIA requirements. There is a long conditioning sequence available if you are not sure that the device can be activated, but for distortion tests, normally it's not necessary, so we won't be running it here.
The jacket hung on the back of the wide chair.
That was conditioning, and here are the noise bursts. In the upper right graph,
The jacket hung on the back of the
from
wide
0 to
chair.
2.4 seconds is the conditioning signal, the sentence. From 2.4 to 6.4 is the chain of
The
noise
jacket hung on
bursts,
the back of
each
the
one
wide
preceded
chair.
by the syllable ba.
Back.
On the left is the spectrum measured from that waveform. The large rectangle is a 1/3 octave band of noise, which is the fundamental. You may see lower level rectangles that are second harmonics or third
The
harmonics.
jacket hung on the back of the wide chair.
In the lower left, you'll see a yellow curve and a red curve. They're both signal to distortion measurements, but of two different kinds. The red is a signal to garbage ratio, where the garbage is everything but the fundamental A weighted, and that's divided by the stimulus level. So it's signal to garbage. The yellow is measuring only the second and third harmonics, but again divided by the level of the fundamental. So it is signal to distortion, but not including noise. If those two are similar, it means that much of the garbage in the device is actually second, third harmonic. If they get to be very different, then you can figure out whether the distortion is dominant or the noise. In the middle lower graph, distortion is represented by another yellow curve, but this time as percent. That might be a bit more familiar. The distortion measurement based on second, third harmonic is not required by TIA, but it'll help you analyze the device and understand where difficulties come from. In the lower right graph is the level of each fundamental versus frequency. It usually follows roughly the frequency response of the device. In the lower center box are the conditioning levels and the distortion test level. Back to the lower left graph with the distortion curves. Above 4 kilohertz, the second and third harmonics of the fundamental are outside the pass band of the system, so they're not measured there. But the signal to noise and distortion is still valid, so it's used. If we look at the distortion versus frequency, we can see that the red curve, the signal to garbage, is well above the tolerance. The yellow curve is also above the tolerance and not too much different. Again, this says that much of the garbage in this device, even though there isn't much of it, is due to second and third harmonic distortion. If we want to know what the overall requirement is it passing, we look at the box just showing now. It's 9 dB above the tolerance, so this device easily passes the distortion test. For information, the distortion is given in percent. Again, this is not required by TIA, but it's here for information. And the level versus frequency. Again, not required by TIA, but sometimes helpful to make sure the device has been staying on through the entire test. We can also have a look at the waveforms for each of those frequencies. It's a good idea to do this, especially if you haven't tested any particular device before. What we're looking for is to see if the device has stayed active through the entire test at each frequency. So in any one of these boxes, you can usually see the conditioning sentence clearly and 10 bursts that follow. That means that the device has stayed active through the test and we have a valid measurement. We can review the curves here and the criteria of passing and failing if we want. We can then go to the saving of the information. We can put it in a simple Excel sheet, or as before, we can put it in the speakerphone master report using this custom addition to the name of the file and putting inside the report any notes that are important for how this test runs. Once the Excel sheets are written, the test report has been updated with this information and the sequence ends. That certainly is a lot of sequences, but remember that a communication device has a lot of different characteristics, and all of them have to be working well if the user is to enjoy the experience of using the device. The sequences can be applied to headsets or anything that is a little bit like a headset, including many wearables, handsets, and speakerphones, or many devices that have a speakerphone function, like smart speakers and that sort of thing. Thank you for watching. Bye-bye.